Um, here we go. I want to talk about just sort of our basic objectives. We did a little bit of analysis on the seismic requirements, but primarily I want to talk about the instrument concept and the spacecraft. There's been a number of pieces of work over the years to think about how to do seismology on small bodies. A lot of the work was aimed at understanding the effects of doing it on a small body that has lots of internal structure. And so I don't want to dwell on that, and the analysis we did is somewhat similar, although more limited. So basically, there's a whole range of bodies scattered through the solar system, and the key question in all of this is what is the internal structure? Are they solid bodies? Are they conglomerates of just loose rubble piles? Are there thick regoliths over broken interiors? Whatever. This is a fundamental question that needs to be resolved in order to understand how these things formed and evolved. The concept we decided to go with was to try to do this with a low energy device. And so we started out with the thumper that was used on the Apollo missions. Essentially what this was a so-called NASA standard initiator, which is a thing that severs bolts and cables on a spacecraft. They drove a little plate into the ground, and they were able to look down to several hundred meters along a fairly long traverse and see the details of the fine structure. Here in the Apollo case, the contact with the ground was made by the astronaut pressing the device against the surface, and so coupling was not a big issue. However, the initiator provided enough energy to make the measurement. Nick Schmer at Maryland has done a number of analyses where we looked at some very simple bodies to understand what kind of frequency propagation we would get and how much energy we would get. He looked at a range of different sizes and a range of different thicknesses of regolith and megaregolith and tried to understand what we would see. Essentially what it shows is that over 180 degrees from the source to the most distant receiver, and again depending upon the size of the body, you can see from a magnitude minus 1.1 to a magnitude minus 7.7, you get energy all the way across the distance. And for comparison, this is the amount of displacement in meters. The Apollo seismic experiment seismometer had a resolution of 10 to the minus 9. So these things all produced the kind of energy that would have been recorded by the Apollo seismometer and would be recorded by the instrument I'm going to show you in a second. So understanding getting enough energy through it is not a problem. But asteroids are not spherical cows. There's a lot of complexity. This is a plot from one of Dan Britt's papers. Essentially shows the macroporosity range, which is indicating a lot of internal variation in the structure. We know there are regoliths on the surface. This is just a thermal inertia as a function of diameter. A lot of these numbers are fairly low, which suggests there's a thick superficial regolith on the bodies, and so coupling the energy into the interior and getting it back out at the other end are critical. So the next step would be to do more advanced models. There are models like this that Martin et al. Did, where they looked at a body that looks sort of like Itokawa and looked at the propagation of energy through the body over 60 seconds. And what this shows is that you start to get reflections and scattering, and it's very complicated extracting the signal you're going to see on the surface in order to understand what the interior looks like. Okay, the sensor that we've been using is a molecular electric transducer system that Hongyu Yu at Arizona State University has come up with. And essentially, this is a schematic of the sensor. Unlike a conventional seismometer, this does not use a mass on a spring. There's no moving parts. The signal is produced by an electrolyte in a cylinder, and as the sensor moves, this electrolyte moves back and forth and generates a current in the system, and that's what detects the motion. There are two little rubber membranes on the end so that you can move the liquid back and forth. The nice thing, as I said, is this is orientation independent. No matter which way you orient it, you'll get a signal. You do need multiple sensors in order to be able to resolve all three components of motion. This is what it looks like in terms of an actual design. This is about a 10 centimeter on the side box, so the whole thing is about this big. It has, in this case, 4 of these sensors, as well as leveling things so we understand exactly what the orientation of the package is. The nice thing about this, as I mentioned, is that it doesn't matter how this is oriented on the surface. It does have to be coupled to the surface, but it doesn't have the requirements that the Apollo seismometer had or that the InSight seismometer has. So the other thing we wanted to look at was what's the smallest spacecraft we could do this with and have a reliable system. And so we looked at a couple different concepts. Some of the work was an extrapolation from the work that was done for the DART mission and some other in-house stuff. But we came up with a design that looks something like this. These pyramidal things are the sensors. We'll come back to those in a minute. This is a camera system. We'd approach look at the asteroid. This is a solar-powered spacecraft. You can see the solar panels folded up here, and there's two, in this case, just for the design, there are two arms on the spacecraft that unfold. When they unfold, this particular version has four, but it's all the same thing. The arm unfolds, the sensor's at the end of the arm. You move up against, I'll come back to this in a second. This is what the sensor that's deployed on the surface looks like. It's fairly small. It has solar panels on it to keep it alive once we let go of it. This includes both the sensor and an active charge. And so we put this down on the surface and we're going to blow it up later. So you can imagine a scenario like this where you move up to the asteroid or the comet, you use this arm, you place the sensor on the surface, you let go of it and back away. You can also jettison the arm just to reduce the mass on the spacecraft. You deploy these around the body and then you can begin the experiment. You could just sit there and wait and listen for any internal activity. Ideally, you'd like to listen for a whole orbit around the sun to see if there's any tidal deformation, but you don't have to. It depends on the situation. You can begin the experiment immediately. And so the way this works is you put these combined sources and receivers around the body, and then the number you have is just a function of how big a spacecraft you want to use, and then you detonate them. And so effectively, you're blowing up a receiver each time you do this, but you get a series of seismic signals through the body, and as you go through this in series, you get a variety of different paths through the body, and you can unravel the internal structure. We also looked at the elements of the spacecraft. For this particular version, which had four of the arms and four of the sensors, the total mass was about a little over 300 kilograms. In this particular version of using an Athena launch vehicle, we could launch 360 kilograms, and so we still had significant margin. We looked at a couple of near-Earth asteroids just as a test case. These are fairly small bodies. They're very easy to get to, which is why they were picked. Going to an object that's farther away just requires more delta V, but we do have considerable margin even on an Athena launch vehicle, so it's simply a matter of adding more fuel and expanding the size of the tanks, and we could go to another body. This is what the dry mass is more or less similar, and the wet mass is largely a difference in the amount of delta V. So in summary, what we've looked at is you can get a very small spacecraft, go up to a body. In this case, all the bodies we've assumed are essentially small enough that they don't really have a significant gravitational field. We're doing this sort of in a zero-G environment. If you tried to do this with this kind of a spacecraft on something like the size of Ceres, it wouldn't work. The spacecraft is not capable of standing off the body propulsively. We'd have to go to a different scheme. But if the body's small enough that it effectively doesn't have a serious gravity, we can work around the body, put the things down on the surface. We also thought about how you might do this on a comet. It's very similar, except for the fact that the comet has this coma around it of dust and gas, and particularly the Rosetta mission saw there was lots of debris around there. So that would complicate it, but fundamentally the concept works. So you could do this on a very small mission at a very low cost and get data that would help you understand the internal structure. The seismometer itself could be used in any environment. There's nothing specific about the seismometer to be used on a small body. This could just as easily be deployed on the moon. Thanks. Dr. Britt.
TRL? What's the TRL?
The spacecraft is...
No, the seismometer.
TRL. Yeah, I am. 5.
5.
No, I mean, the individual components have been built. Actually, a benchtop version was taken to Iris and put down on a pier with other seismometers, and it detected signals, already understand the noise. So the real issue is, which is not trivial, is to turn this into a flight version.
What's your magnitude detection on the seismic signal? 1.5, 2?
In what units? Magnitude?
Yeah.
Oh, negative, -3,
Okay.
-4. I mean, it's better performance than the Apollo seismometers, which was 10 to the -9 microns, meters, a couple of microns.
Thanks. We'll continue these questions later on this afternoon.